A warm evening to everyone. So, welcome to this session on day two. And today we'll be uh, calculating some of the parameters, some cell parameters. So, we'll be performing some theoretical calculations, some like cell voltage or total cell potential, cell energy, and cell capacity. And also, we will try and see if we can get some brief numbers on the total number of cells in a battery pack. Yeah. So with that, we will just explore the theoretical calculations. Yeah. So for today, these are the parameters that we'll be calculating. So we'll start with total cell potential, where we'll use the Nernst equation to find out the total cell potential. And following that, we'll also find out the capacity and the energy. Yeah. And then finally, we'll have a brief look at how to find the number of cells of a battery pack. So before we proceed into the calculations part, so first we'll take a look at what exactly is reduction potential and oxidation potential. So these two terms are important to understand the reduction and the oxidation potential of a particular cell. So basically, reduction basically is a process where any material starts to gain electrons, and oxidation is a particular process where a particular material starts to lose electrons. Yeah, and the particular terminology potential, defines to what extent can a material undergo reduction and to what extent can it gain or lose electrons. Okay, so that's what reduction potential means. So a higher reduction potential corresponds to material's ability to gain electrons easily. So that means the more positive the value, the more easily it can gain electrons. And lower reduction potential would mean the material has a good ability to lose electrons easily. Yeah, so that we will see in the electrode potential chart in the next slide. Yeah, so this is the simplest definition of reduction potential and oxidation potential. Okay, so oxidation potential is nothing but the opposite of reduction potential. So a low reduction potential would mean a high oxidation potential. Yeah, so that's what is a simple terminology, what these two mean, and that's the difference between these two terms. Yeah. So how exactly will we find the reduction potential or the reduction capacity? Basically, it is found out by subtracting the respective potential of the electrodes. Pardon me, there is a mistake here. This should not be cathode. Here, this should be anode. Please make a note of this. This should be E cathode, that is potential at cathode minus potential at anode. Okay, so there is a mistake here. This should be anode. So that is what is your standard reduction potential of a particular cell, an electrochemical cell. Okay. So whatever equation that you see here, this particular equation that I've highlighted, this is applicable to 1 mole concentration of electrode material. Okay. So in order to understand what is molar concentration, you have to know that the anode and cathode of a cell is made out of something called as active material. Okay. It's made of something called as active material. All right. So this active material is nothing but all of your elements that comprise of the entire electrode. So basically, let's say if you're taking up a lithium cell, so its active material would be lithium, some metal, and its oxide, all put together with binders and additives and separators, and all of these put together will give you the active material. And likewise for the cathode also, you will have active material like graphite mixed with lithium and carbon as such. Yeah, so that is what is meant by electrode material, and 1 mole concentration of this is basically 1 mole amount, 1 molar substance of each of this material. Okay, I will not be going in depth into molar concentration and all of these, but it is just important for you to know at the molar concentration for 1 mole concentration, this equation is applicable. Okay, the equation that I've highlighted here. Yeah, but for different molar concentrations, we will have to use something called as Nernst equation. Okay, which is derived from Gibbs free energy equation. So that we will look at in the upcoming slides. Okay, so this is the standard definition of reduction and oxidation potential. So please do make a note of this. It is important to understand what exactly is reduction potential and oxidation potential. So from this, we'll actually be able to understand what are the different reduction and oxidation values or potential values from the chart. Okay, so that chart you can see in the next slide. So just I will move in a minute so they can just write all of this down and then I can proceed. Okay, so let's proceed to the next slide. Yeah, so on the left hand side, you can see this is what is called as a standard reduction potential chart. Okay, so what this particular chart shows, how easily a particular element can either accept or lose electrons during a particular chemical reaction, which is standardized at 25 degrees ambient temperature, 25 degrees Celsius ambient temperature. Okay, at 1 bar atmosphere. Okay, so this is standard temperature and pressure, STP. And at this two values, all of the potential values that you see here of each and every element, it is rated at this temperature and this pressure. Okay, so maybe you can just take either a screenshot or you can just write down these values. So it is important because we'll be taking few examples from this. Okay, so what we'll be doing is we'll be referring to the Nernst equation that you see here. This is the Nernst equation, and we'll be using this to derive the total cell potential of the cell. Okay, so we will first explore the Nernst equation. We'll understand one by one what exactly the Nernst equation has, all of its terminology, all of its comprising parameters, and then we'll take a simple example of zinc and copper. Okay, so the same Daniel cell example that we had seen yesterday. So we'll take that same example and we'll calculate its total cell potential. Okay, so the Nernst equation comes basically from the Gibbs equation. Okay, so it comes from the Gibbs equation. Okay, Gibbs equation for free energy. Okay, so the derivation of this equation is pretty simple. So we'll just quickly go over that and then we can start with the example. So we know that a Gibbs free energy equation gives basically how much work a particular cell or a particular chemical element can perform based on the number of electrons participating in a reaction. Okay, so delta G, so Gibbs free energy is given by delta G is equal to delta G naught standard free energy minus RT ln K. So this is the standard Gibbs free energy equation. Okay, so this is what is called as overall free energy. This particular term here, this one is here. This is called overall free energy, and this one is called standard free energy, and this one is the product of universal gas constant and the ambient temperature T, and the logarithm, the natural log of something called as the reaction quotient. Okay, so that I will explain exactly what is reaction quotient. So this is the basis of the equation, and then further on, if we simplify this, so we know delta G is a product of number of electrons participating in the reaction, the Faraday's constant, and the cell potential E. Okay, so basically delta G is equal to NF into E of cell. Okay, so E cell is nothing but the standard or total potential of the cell is equal to NF E naught cell. So E naught is the standard potential of the cell minus RT ln of K. Okay, so this is how we will derive the equation. And then further, if we have to just simplify this equation, it's just we take NF from the left hand side to right hand side. So then what would happen is NF gets cancelled over here. So for these two terms, NF will get cancelled, and then it would become RT by NF. Okay, so like please do mention this in the new line. I don't have space, so I'll just be writing it like this. So then it would then become E cell, which is the total cell potential, is equal to E naught of cell minus RT by NF into ln of K. Okay, so this is your final derivation of how the Nernst equation will be. This is how the Nernst equation will be derived. And now this is how the total cell potential will be calculated. Okay, so just take a minute or two to just write this equation down, and then we'll proceed with the understanding each term, and then we'll get the some example. We'll just look at this example: zinc and copper. Yeah. Yeah. All right. So I will now clear this. Yeah. So now we'll understand each of the terminology over here in this Nernst equation. So E cell will be your total cell potential, and E naught of cell will be the sum of standard potential or also reduction potential. It's that same equation that we saw in the previous slide, where we saw E of cathode minus E of anode, and that is exactly what will be E naught of cell. And then R will be your universal gas constant, which is fixed at 8.314 joules per Kelvin per mole. Okay, T will be your ambient temperature. Usually it will be taken at 25 degrees Celsius, which is 298 Kelvin. L is the number of atoms, not atoms, and is the number of electrons participating in the reaction. It is not atoms, it is electrons participating in the reaction. And F will be your Faraday's constant, which is approximated at 96,500 coulombs. Okay, and then K will be your reaction quotient, which is basically a ratio of active material concentration. So whatever material concentration we have for cathode and anode, if we take the ratio of them, we get the reaction quotient K. Okay, so this is how we will be looking at each of the term. And let's proceed with a simple example. So we will take the same Daniel cell example that we had yesterday, right? So consider the zinc anode and copper cathode. Okay, so you can just please note these values down. So please keep a calculator and some pen or paper at hand right now. So we'll start with the calculation. So consider zinc as anode and copper as the cathode. Okay, so from the reduction potential chart, which we saw previously, we know that zinc's reduction potential is at minus 0.76 volts. Okay, so this is at volts. And copper's reduction potential will be at plus 0.34 volts. Okay, so please do note these values down. And also, you can note down the anode molar concentration values, anode and cathode molar concentration values. Okay, so this will be 0.05 m molar, m is for molar, and 0.085 molar. Okay, so this is your active material concentration. So with these values, we will now proceed to calculate the E of cell, E cell, that is the total cell potential. Okay. So yeah, let's go to the next slide. Yes. So total cell potential. So let's write down here. E naught of cathode will be 0.34, right? Minus 0.76, right? So what is the sum of this? What is the final answer? It should be 1.1 volt. So this should be your standard cell potential E naught, and this is the value E naught that we'll be using over here in the final equation. Yeah. So what we're going to do now, so we're going to calculate. So E cell is equal to 1.11 or 1.1 volt minus 8.314 into 298.15 divided by 2. So n here will be 2. So how exactly it is 2? Let's just write down that equation over here. So yeah, I will just write this in a different color. So we know oxidation, what will happen? You know, oxidation is zinc loses 2 electrons, so that becomes zinc 2 plus 2 electrons, right? And reduction will be copper gaining 2 electrons, right? So in both oxidation and reduction, you can see overall there will be a total number of electrons of 2, right? So this is why n is equal to 2. Okay, so for that purpose, in the denominator over here, n will be 2. Okay, so F, we know F is a fixed constant, so that will be 96,500 coulombs. Okay, so this will be your E naught cell minus RT by NF, right? So now what we have to do, we have to calculate K, right? So please note this down. So K is equal to the ratio of cathode molar concentration by anode molar concentration, right? So that is going to be 0.85 by 0.05. Okay, so please calculate this value and put this up in the chat box. Let's see what the value we get here. It should give you 15. No, sorry, it should give you 17. Right. So now we have all of the parameters at hand. So now it's going to be 17, ln of 17. Okay, so it's not log, it is ln, natural log, ln. So in your calculators, you might see an option of ln. So please use that. And your final option, your final answer, yeah. So your final answer will now be so 1.1 minus 8.314 by 2002 into 96,500. So you should get an answer of 1.061 volts. Is everybody getting that answer? K is, again, as I said, K is what is called as reaction quotient. And K is basically the ratio of the cathode molar concentration to anode molar concentration. So in the previous slide, I had shown what exactly are the molar concentration values. So for cathode, it is 0.85 moles molar, and also for anode, it is 0.05 molar, right? So if you take the ratio of that, that will give you K, okay? And that value will substitute over here. Okay, so by substituting, you should get this answer. I think 1.061 volts is the answer for the total cell potential. Is everyone finding the same value? Yeah, I see 2 answers. Yes, that is correct. Okay, so I hope everyone is following. So if I'll just repeat this once again. So you will calculate their total cell potential using something called the Nernst equation. Okay, and that Nernst equation will start with calculating the standard cell potential E naught. So if you have the two cell reduction potentials of the anode and cathode, you can find out the standard cell potential. So you just substitute the values of E cathode and E anode in this equation, in this particular equation over here. So if you substitute the values, you'll get the standard cell potential, but that is not the final answer. You have to also account for the change in molar concentration of the material. Yeah. So for that purpose, we'll also take the logarithm of this, the natural log, and then we'll take also the Gibbs, we'll also account for Gibbs free energy change. And that is given by this RT by NF. Okay. So N is 2. We saw from the reaction that N is equal to 2. So 2 electrons are participating in the reaction. And if you substitute all the values, we get 1.061 volts. Yeah. So please keep this value with you because we'll be needing this in the upcoming calculation as well. Okay. So let's progress to the next one. So here we will calculate the cell capacity. Okay. So in order to calculate the cell capacity, you have to use this particular equation. Okay, this is called the theoretical cell capacity. Okay, this is called theoretical cell capacity. And why exactly this is called theoretical cell capacity? Because it does not account for the mass contributed by the additives, the binders, the separators, and some amount of electrolyte material being gelled into the cathode and anode, and also some of the like other components of the cell, like the current collector and as such. Yeah, so that is why this is called theoretical cell capacity. It is only a theoretical value and it is not the actual value. Okay, so we will calculate it by using this simple equation. So NF by M. So we already know what is N, and we already know what is F, right? So if you substitute the number of electrons participating in the reaction, the Faraday's constant, and the molecular mass of the active material, right? So that's what is M cathode. Basically, M cathode and M anode respectively is the molecular mass of the particular electrode. Yeah, so that you can see the values are given over here. So these two values. Okay, so this is the molecular mass of zinc, which is at the anode, and of copper, which is at the cathode. So if you substitute these two values in the above equation, so let's write this down. C cathode equal to 2 into F, which is 96,500 coulombs, divided by M cathode, molecular mass of cathode, which is 63.4. Okay, so we will write here 63.4, and the value of this should be 3044.17 milliamps. Okay, so your answer will be in milliamps, not amp hours. It will be in milliamp hours. Okay, so this is for the capacity at the cathode. Okay, this is only the capacity at the cathode, and for anode we will write separately. So C anode, I'm writing here on the left hand side. C anode is equal to, so your numerator will stay the same, 96,500 into 2 divided by 65.8. Yeah, so this should give you 2,934.1 milliamp hours. Okay, so these are the two values that we'll get for the capacity at the anode and capacity at the cathode. Okay, so now substitute this into the final equation that we see at the bottom over here. So let me just erase this part. So yeah, now you can see this better. So just substitute these values in this final equation over here. Okay, so your final answer will be, so what would be the final answer? Yes, that is correct. 1.45, 1,1494 milliamp hours. Okay, it is milliamp hours, not milliamps, milliamp hours. So this will be your final cell capacity. Okay, and please do keep this in mind that it is for these specific molecular masses. Okay, again at 25 degrees Celsius. Okay, so this will be your cell capacity. So you can write this down. Cell capacity is 1,494 milliamp hours. Okay, so this will be your this is how you calculate your cell capacity. using this particular equation. So again, let me reiterate this, that this is the theoretical cell capacity and not the actual capacity. Your actual capacity will be a little bit different because your molecular mass is not just from the active material, but also it is from the binder agent, from the additives, from the separator, from the electrolyte material inside the gelling with the cathode and anode, and also some bit of current collector and some other material which will be adding to the which will add to the molecular mass. Yeah. So this is how you find out the total capacity. Yeah. Uh, the one at the bottom, uh, for the person who's asking, the total capacity is given by the bottom equation, this one. Yeah. So uh, let's move on. I hope everyone is able to follow. So I will now be proceeding to the next one. So cell energy, right? So we have found out the total cell potential, right? So we found out to be 1.061 volts, right? And into cell capacity, we just found that out to be 1.494 amperes, right? So if you multiply this, you'll get your total answer in watt hours. Yeah. So if you do the math, you would get 1.58. 1.58 watt hours. Okay. So 1.58 watt hours. Always, it's not in kilowatt hours. Please don't get confused. It is in watt hours. Okay. So your answer will be in 1.58 watt hours. Yes. So I hope that you have all been able to follow so far. So with these three are the primary parameters. So you can just write it down. So cell voltage or cell potential, 1.061 volts, cell capacity, which is 1.494 amperes, right? And your energy will be 1.58 watt hours. Okay, so this is your three parameters that we have calculated so far, right? So now a little bit of calculation which you will do from your side. Okay, so I will provide the equation and I will provide the values. Okay, this will be practical calculation which all of you will do. Okay, and please let me know what answer you get. Okay, so I will clear the screen now, right? And I will now provide values for you along with the reaction. Okay, so let's take an example of LMO. Okay, LMO, basically LMO is lithium metal oxide. Okay, I am just broadly classifying this as lithium metal oxide because, like in the case of LMO, many number of metals can be used. So aluminum, magnesium, manganese, or copper, tin. So many of the metals can be used, right? But if you want exact types of material, it would be manganese, cobalt dioxide, and all of these kind of materials. Yeah. So let's take a look at the reaction, and it is given by the following reaction. So please do note down the reaction. So at anode, so we know at anode reduction happens. So please note down this. So at anode we have lithium carbide, which is given by LiC6. It is oxidized into lithium ions. So that is 2 lithium ions plus 2 electrons plus carbide. Okay, C6 is given by carbide. Okay, I mean carbide is given by C6. So basically, this is your carbide ion. Yeah, and this total potential of this particular reaction is given as minus 3.04 volts. Okay, so this is the total potential of it. And at the cathode, okay, so here we'll write the cathode reaction. Cathode. So cathode will be a reduction. So the same lithium ions that you see that were given out from the oxidation reaction will be used here. So 2 lithium ions plus 2 electrons plus the metal oxide. Okay, so this portion, the metal oxide, which is given by manganese dioxide, MnO2, gives Li MnO2. Okay, so this is your reaction at the cathode. Okay, and this has a cell potential of, I mean, this has a total reaction potential of 1.07 volts. Okay, and also looking into the concentration. Okay, I'll also provide the concentration and also I'll provide the molecular mass. Okay, so concentration for lithium manganese dioxide, this is a concentration of 0.1 moles, 0.1 molar concentration. And here at the anode, for lithium carbide, the concentration is 0.02 molar. Okay, so we know now the cathode concentration and anode concentration. And one last thing, that is the molecular mass. I will provide that. So molecular mass at the cathode, the molecular mass is given by 180.7. Okay, so 180.7 grams. And here at the anode, it is going to be 78.97 grams. Okay, so now we have the reaction, we have the number of electrons participating in the reaction, you have the molar concentration, you have the molecular mass, and also you have the standard potentials for both the anode and the cathode. Okay, so with these values, now you will perform the calculation, and please do type it in the chat box. Let's see what answers we get. So you can take 5 to 10 minutes to just find the total answer. And again, please do remember to use natural log, not logarithm, not log. It should be ln, natural log. No, I'm just waiting for answers from everyone. Am I clearly audible to all? Can you all hear me?
Yes, you're audible.
Yeah. Just pause. I have just paused the reaction for now. I mean the recording for now, so
Yes.
that they can just give the answers, and then I'll resume.
Okay. Thank you.
Yeah. Sorry, I didn't understand your question. Kuruba, I did not understand your question. Please, could you repeat? No. So whatever I have provided are for the anode and for cathode. This is not the total cell potential. So like what you see here, minus 3.04 and 1.07. These are for anode and cathode. From this, you have to find the total cell potential. Vandana, what do you mean by electric parameters? Voltage, current, and temperature. No. Don't get that confused. That is for the entire battery. And please don't confuse that over here. This is specific to the anode and cathode. You can. So can you repeat cathode and anode molar concentration? So yeah, the values are right here. This is for the anode. Let me just highlight that. This is for the anode. And this is for the cathode. Okay. Oh, 0.10 E cell. Yes, that's correct. Please add at least one more decimal to it. So let there be like 3 decimals. So then we can, I think the correct answer would be 4.1098. That must be the correct value. What about others? Are others also able to find the same value? Yeah. Yes. E, R, and F values will be staying the same. K is equal to 5. Yes. Okay. So any other answers? Another person has had here E cell is 4.11. Yeah, that is correct. That is almost the correct value. You would get something like 4.1098. Yes. Yeah. So one more thing, if you would like to, if anybody is interested to see here, if you change the number of electrons participating in the reaction, you will see that your E cell actually starts to rise up. Okay. So that is something you can just take it, try to see as an assignment, and also try and see for slightly different electrode compositions. Yeah. So okay. Yeah, I think we have spent enough time on this. So your correct answers for this would be E cell is equal to 4.0981 volts. Okay, so this will be your total cell potential, and this is for the particular molar concentration that has been given here for the cathode and anode. By varying not only the concentration but also your active material mass that you see over here, this portion here, these materials, of course, they will change. They will not stay the same throughout the entire reaction. They will keep changing. And also your number of electrons participating in the reaction. So here we have seen an example of 2 electrons, right? But if you consider a case where you have slightly higher number of electrons, you will see that your total cell potential actually goes up. Okay, so basically, as I had said earlier, so more number of electrons you have, higher the potential you have available. Okay, so also it is, you could use higher number of electrons, but again, on the downside, if you use too many electrons, then your cell will get damaged pretty quickly. Yeah. So this is how you would find out. And same with goes to your cell capacity and also your cell energy. Okay, so your capacity, you can calculate it using the formula that I gave you, NF by M. So what is the capacity that is obtained? So can somebody see cell capacity? Can anybody already has these answers. So what would be your total capacity? If I'm right, it should give you 756 amp hours. Sorry, milliamp hours. So your capacity will be 756 mAh for the given mass that I have given over here, the molecular mass for anode and cathode, right? So that will give you around 760 mAh, right? And yes, as the person pointed out, thank you. Yes, the answer is correct. The energy will be 3,107 watt hours. Yeah. So this will be your answer for this lithium metal oxide. Yeah. So these are the values. So I hope everyone has followed. So any yeah, that is a close answer. 7,432.08. Yeah, little bit of variation will be there in the answers, so that's fine. So shall we proceed? We'll proceed to the last two sections to find out the total number of cells in a battery pack and also the mass of the battery pack. So we'll proceed to that. Has everyone been able to follow till now? Okay, great. So let's proceed to the next topic, right? So in a battery pack, you would have to find out two parameters. One is called the number of cells in series, and the other one will be your number of cells in parallel. Okay, so your number of cells in series is first and foremost dependent on the main parameter that it is dependent on is what battery pack voltage you're trying to design it for. Okay, so let's say, just as an example, let's say I'm trying to design a battery pack voltage of 48 volts. Okay, so just as an example, let's take 48 volts as the battery pack voltage, right? And an individual cell voltage. So from the lithium ion cell example that we derived earlier, so we derived a cell potential of roughly 4.11, right? So if you were to derive the total number of cells in series, what would this be? This would be something like almost 12 cells. So it will give you an odd number, 11.73, but it would you just have to round out off to 12. Okay, so number of cells in series will be 12. Okay, so this will be 12 cells in attached in series. Okay, now you have to find out the number of cells in parallel. Okay, number of cells in parallel. So here also, let's assume an example. So let's assume that you are designing a battery pack of 2 kilowatts. Okay, so we're assuming that we are designing the battery pack for 2 kilowatts. So that's 2000 watts. Okay, divided by individual cell power. So cell power will be nothing but your voltage into current, right? So your voltage is 4.11, right? And let's assume that it can give a maximum current supply of 2 amps. Again, let's take that as an example here. So 4.11 volts into 2 amps into number of cells in series. So whatever value we found over from here. Okay, so 12. And for this, your final answer would be, so that's 2000 divided by 12 into 2. So that's roughly 21 cells. Okay, so 21 cells in parallel. Okay, so this is how you'd be able to easily calculate how many cells you want in series, how many cells you want in parallel. And then if you take the product of these two, so we have 12, we have 21. If you take the product of these two, we'll have the total number of cells required for a battery pack. Okay, so let's do a simple calculation here. So that should give you around 252 number of cells. Okay, so usually we won't stick to this exact number. It's not that, okay, we got 252, we'll stick to exactly 252. We have to give some margin, right? Some safety margin must be there. So we'll take roughly 260 cells. Okay. So this is because we have to have some safety margin. So we'll have 260 cells. Okay. And this is how you'll find the total number of cells in the battery pack. Okay. So has everyone found out? 2 amps is the current. Yes. I've just arbitrarily assumed that one cell is supplying 2 amps. So your total power would then be 4 volts into 2 amps. Yes. So yeah, as I said, 2 amps will be like arbitrarily, I'm assuming it to be 2 amps. You can feel free to choose whatever current value you wish to. But I have assumed that for a particular cell, it's a low power cell. So about 2 amps is the maximum power, maximum amount of current it can supply. Okay. So I have chosen 2 amps to be just as an example value. And then you can just find out your NP, number of cells in series, and number of cells in parallel, NP. Okay, so with this, we find out the total number of cells in a battery pack. Okay. So I'll proceed to the last part of our calculation. So over here, so we will now find out the mass and volume of the battery pack. Okay, so we know, if you see any data sheet, if you see any cell data sheet, say for example a lithium ion, any specific data sheet, you will see that particular type of cell called 18650. Okay, so these are one of the most commonly used lithium ion cells in the market. Okay, they're cylindrical type. Basically they're like similar to your AA batteries, but like of course their nominal voltage will be a little bit different. So in the data sheet, it has been like usually it'll be specified that 186 the cell will have a mass of 45 grams. Okay, so yeah, if you convert this to kgs, it's 45 by 1000, which will be 0.045 kilograms, right? So now your total mass will be your mass of one cell, which is 45, 0.045 into total number of cells. So which we saw in the previous example, it will be 260, right? So if you calculate the mass of your battery pack using this, so what will be your final answer? So that will be almost 12 kg battery pack. Yeah. So yeah, 11.7 is the answer. That's correct. But you can just round that off to around 12 kilograms. Yeah. So that is for a total number of cells of 260. Again, if you if you're interested, if you can see that your total number of cells will vary if you change your number of cells in series by increasing or decreasing your your total battery pack voltage and also your individual cell voltage. Yeah. So the example that I gave you of the lithium ion cell, it is for a lithium metal oxide, so which is specific to lithium manganese dioxide. But if you choose for lithium iron or lithium iron phosphate, then it is its properties will vary, and you'll see that your battery actually becomes a little bit heavier. Okay, so like that you can just see for different values. Okay, so this is your mass of the battery pack, 12 kg. Okay, and so now we'll see the last parameter. So volume of one cell. So one cell, 18650 cell. Okay. So we have to take the volume, which is given by pi r squared h. So we know like the radius is nothing but diameter by 2, right? So the diameter is given as 18 mm. Okay. So for standard, for all 18650 cells, your diameter will be 18 millimeter, right? So then your radius will be 9 millimeters. So convert this to meters, right? So 9 by 1000, which is 9 into 10 raised to minus 3 meters. Okay, so that will be your radius. Your height will be 65 millimeters, okay, which is nothing but 0. So 65 by 1000. So 0.065 meters. Okay, so now we'll find the volume of the cell. So just go ahead and multiply pi r squared into h. So pi into 9 into 10 raised to minus 3 into 0.065. Okay, so you should get a volume of 1.65 into 10 raised to minus 5 meter cube. Yeah, so this is the volume in meter cube for one cell, right? So if you were to find out for the total number of cells, it would then just be 260 into the answer you have derived till now. So 260 into 1.65. Yeah, so this is going to be your final answer, which is 4.3 into 10 raised to minus 3 meter cube. Okay, so you can also convert this to liters. So we know that 1000 liters is 1 meter cube. So so that's roughly, if I'm correct, so that should be around 4.3 liters. Yeah. So 4.3 liters. So always make sure that you convert your total volume to liters. Okay, it is okay if you keep it in meter cube, but usually it is expressed in liters. Okay, so I mean, if because you're trying to compare a fuel tank of an IC engine car to that of a battery pack. Yeah, so your total volume will then be 4.3 liters. Okay, so I hope everyone has followed till now. Has everyone obtained this answer? Somebody has mentioned here, it is 10 raised to power minus 5. No, if you take, okay, so see, 1 meter cube is equal to 1000 liters. Okay, so now if you substitute this 1000 liters here, so that's going to be 10 raised to 3 into 10 raised to minus 3 into 4.3. So that will give you 4.3 liters. Yeah. So convert whatever answer you have in meter cube. So please do convert that into liters. So that is standard. That is how you express it. Okay. So I hope everyone has understood up until now. So these are how basically you will find out the total mass of the battery pack and total volume of the battery pack. Okay. So yeah. Okay. So whatever we have done up until now, it is purely theoretical calculations. Yes, definitely there will be some variations. And probably as some assignment or probably as some sort of a homework, maybe you all can try all of your values for lead acid. Okay, so whatever I've shown you till now is for a lithium ion battery. So you can just try it for lead acid cell as well. Okay, try to see what you can find over here. So your individual cell voltage for a lead acid battery would be something close to about 1.9 to 2 volts. Okay, data sheet right now I don't have one with me. Let me see what I can do about it. Perhaps we have another session tomorrow, so maybe I can provide you with that sheet. But you can try with slightly different values for lead acid. Okay, so you can just see as an assignment. So lead acid. Yeah. So lead acid, and even you can just try for nickel cadmium, NiCd. You will see that there'll be a very drastic difference between the battery pack weight, especially for lead acid. You will see that this will be like something like 50 to 60 kilograms or maybe even more. Yeah. So you can try for this. I will try and see if I can provide some data sheet to you people. In fact, I think we are just running short of time for today. So tomorrow's session, I'll just try and see if I can provide some info. So yeah, thank you all. This is the last session for today. So thank you for attending today's session. I hope that everyone was able to follow. So now it's time to have some Q&A. So let us